One of the big parts of inductive reasoning is looking for algebraic patterns. So we'll give you a sequence of numbers and we'll try to have you find the relationship. So in middle school, you actually used input-output tables where the input was the x and the output was the y. And you were able to determine expressions for those in sequences and series. So the first step to finding that pattern, and you were able to do this in middle school, is you need to identify the variable that is the input. That is, what is n. Now, if we have a table, it's usually the first value in the table. That is your n. If there is no obvious table, then it could be the position number. So if it's a number, if it's a group of numbers in a row, each position would be the number for n. So position 1, n is 2 for position 2, n is 3 for position 3. Now, the second thing you have to do, and this actually goes on 2 slides because there's so many things to try, you're going to look at how the output changes as n increases and try different operations until you are able to get the same output. So if it's a linear relationship, which is a lot of what we studied, you want to look at the ratio of the difference in output to the change in the input. All right, so if it gets bigger with each increasing, there's probably a multiplicative ratio. So if it's a constant, try multiplying that ratio by whatever n is. If the ratio is not constant, try modeling the expression using n and multiplying that expression by n. I know it feels complicated. I'm going to show you an example. Don't lose your steps. Other things you can try. If the others don't work, try a power of n, like n squared or n cubed. Normally, we don't do a lot of powers of n, so I don't expect it, but you might end up with that. And for all of the above, you may need to still add, subtract, multiply, or divide by a constant to get it to match up just right. Usually it's an add or subtract if it's a linear relationship. Finally, check your expressions by substituting at least 3 of the inputs for n and check it against the outputs. So let's look at example 3. Find the next 2 terms in the pattern. And then I want you to find the expression for the nth term. So that's something that you can use to predict if n is 100 or 200. So it's like a general rule. Now you may wish to use the table to find the expression. So if I just gave you the first part of this problem, it's not very hard. You can already see, looking at it, what happens. We do 3, 8, 13, 18, 23. You might say, oh, well, it's always ending in 8 and then 3. Looks probably that's going to be 2, 8. You might notice there's a difference of 5 between these. It's always going up by 5. So there we go, 28. So that would make that 33. So that part's pretty easy. Now let me put the input for n. This is position 1. So 1, the output was 3. On position 2, we had 8. Position 3, we had 13. Position 4, we have 18. And position 5, we had 23. So we know that these increase by 5 every time. So what we should do is try multiplying the input times 5. 5 times 1, all right. 5 times 2, right? And then we have 5 times 3. 5 times 4, and 5 times 5. All right? Well, when I did this, 5 times 1 is 5. I'm high by 2. If I took away 2, that would work. Let's see. 5 times 2 is 10. I'm too high by 2 again. 5 times 3 is 15. Oh, if I subtract 2, that would work. 5 times 4 is 20. If I subtract 2. So it's minus 2 every time. So I multiply the n by 5 and then subtract 2. Now, how do I get a rule from this? See this part right here? Let me go ahead and highlight that. That part is the input n, this part right here. So that's the part changing from input to input. So the output is 5 times n, minus 2. That is the expression for this pattern. On example 4, we ask you to complete the following conjecture. You may wish to use a table. So it says a number of segments formed by n collinear points. So here they're telling us the first column in the table is n. So somehow, let's take a look at the difference. All right, so the difference from here to here is 2. The difference from here to here is 3. And the difference from here to here is 4. It's not staying the same. In fact, the difference at 3 was the old n. So the difference was actually n minus 1. That was a difference. So, oops, sorry, let me erase this. So you can see the pattern better. I'm actually, instead of n, I'm going to say what it was, okay? Pointer options, pen. So here it was 2 minus 1, excuse me. Here it's going to be 3 minus 1 for that difference of 2. For that one, it was 4 minus 1, because I want to relate it to this number. I want this number to show up here if I can. And this difference was 5 minus 1. All right. So if I do this, this gives me 2. I could try multiplying it by n, right? If I go, that would be 2 times 3. Let's take a look at this. Multiply it by n. Multiply it by n. All right. Okay. 2 minus 1 is 1 times 2 is 2. Okay. That's a 1. Maybe I just need to add, subtract a 1. Let's try it. So here I'm getting a 2. Here I'm getting a 6. Here I'm getting a 12. And here I'm getting a 20. Oh, do you see the pattern here? Let me try to highlight that for you. This is a tricky one, so don't worry if it's giving you a little bit of trouble. All right? This is a nonlinear one, and these are more challenging. See the 6 and the 3 and the 2 and the 1. You'll notice that currently what this is doing is it's making my output twice as big. So if I could cut it in half, then I could get it to match. How can I cut it in half? I could just divide by 2. Divide by 2. Divide by 2. And I will get the right number. So that means for my rule, it's going to be n minus 1 times n divided by, pretend that's a divide by 2. So the number of segments formed by n collinear points is n times n minus 1. Or you can switch them, it's okay. Commutative property, by the way, divided by 2. In our last example, this one's a little more straightforward. I have a triangle, and it has 3 sides. And we know it has 180 degrees. You probably learned in 6th grade that, and you should have, there are 360 degrees in a quadrilateral. And your teacher may have shown you there are 540 in a pentagon and 720 in a hexagon. There's actually a relationship between these. This is my n right here in the center. So this is n. And let's take a look at how the output changes from one to the next. It's always increasing by 180. So, if I did 3 times 180, that would be too big. I could try it. I could try 3 times 180, and if I subtracted 360, that would work. And actually, 4 times 180 minus 360 would work. But that's not one of our patterns. This actually does work. And one of the patterns down here matches it, but you may not recognize it. Try plugging in different numbers. 180 times 3, that would be too big. You just put in the number, right? You get 540 on your calculator. 3 plus 180, that's too small. Or actually, it's too big. That doesn't work either. All right. 180 times 3 minus 2, which would be 180. Because 3 minus 2 is 1. 180 times 4 minus 2, that would be 2. That would be 360. 180, I'm going to bring this spot over here. 180 times 5 minus 2, That would be 180 times 3, which is 540. So far, C looks like it's working. Let's try one more. 3 plus 2 times 180. Well, that would be 5 times 180, and that would be, what, 5 times 80, 400, 900. That's wrong. So your answer in this case is C. So there are times that you will be given a table and seeing which rule works. Those are the easiest problems. There are also times where you have to come up with a rule. Most of the time we try to keep it to linear, but sometimes you might see nonlinear, which is like that n times n minus 1, which is more complicated. So what we would like you to do for today's lesson is to write 2 conjectures of your own in complete sentences. They do not have to be geometry or math conjectures. So just say, this must be true based on observation.